Welcome to section 6.7, enthalpy. The learning objective for this module, perform calculations related to heat flow for chemical reactions. You probably are not familiar with the word enthalpy. We're going to use kind of a loose definition here. Enthalpy is the heat flow when a reaction occurs at constant pressure. Don't worry too much about the constant pressure aspect of that. Anything where we will be using it in this course, that will always be the case. You can think of enthalpy as sort of a fancy word for heat, and that would be a good way to understand it. We looked at these ideas earlier in the course, but I want to remind us of how this works. Something is exothermic if energy is flowing out of it as the reaction takes place. We use this symbol. This is again the Greek letter delta, the triangle, delta H of reaction. So H is enthalpy. You can think of it as meaning heat. So the change of heat of the reaction is negative. So energy is flowing out of the reaction as it takes place. So the reactants have a higher energy than the products. In an endothermic reaction, energy is absorbed as the reaction takes place. So the products are a higher energy than the reactants. Delta H is positive in this case. Be aware of the difference between exothermic and endothermic reactions, both in terms of where the heat is flowing, how the reactants and products are compared comparatively based on their energy, and the sign of delta H associated with that transfer of energy. I wanted to say a few things about energy and chemical bonds before we look at some calculations. It is always true that energy is released when a stable chemical bond is formed between atoms. That is always true. So forming a bond always releases energy. There are some reactions where it looks like that is the opposite of what's happening. And the reason for that is there are several bonds breaking and forming at the same time, and you might only be focusing on one of those. So if it looks like it's requiring energy, it's because you are forming bonds that are stronger at the expense of weaker bonds that are being broken. So just be aware of this. You might see some shorthand in terms of how this is explained in some of your other courses, but just be aware that this is always true. We can do calculations when we consider the flow of heat. We do this by showing an equation that contains a term that indicates the amount of heat that is exchanged as the reaction takes place. Let's look at the example and then we'll talk about how this works. So here we're showing a balanced equation in which we have this delta H term. You would have to be given all of this information. There's no way I can expect you to just come up with this number. It will be always be given to you in this class. What you can do with this number is you can pair this number with any of the coefficients of the balanced equation. And you would then use it as a conversion factor to find the amount of heat related to the amount of a particular reactant or product in that reaction. So you're pairing this number with the coefficients. Okay, so these are in terms of moles. This is in terms of, we're showing this in terms of kilojoules. Often it will be kilojoules. You might see joules on some occasion. I think almost all the time it would be kilojoules, however. So let's go ahead and do an example problem. Feel free to pause your recording and try this on your own, and then we'll come back and talk about how to do it. how much heat is consumed when 12.5 grams N2 reacts. Okay, so let's write down some information. We're given grams of N2, so we might need to know some things about N2. So we know that 1 mole of N2 is equal to 28.02 grams. Okay, so that's a calculation you can do from the periodic table. The other thing we know is, well, we're looking for how much heat. The other thing we would need for that is we would need this information. So we can say if we look at the balanced equation, we have 1 mole of N2 in the balanced equation. So we can say 1 mole N2 is equal to 181 kilojoules because this is equal to any of the coefficients. If we were looking at NO, we would use a 2. We're using a 1 because we're looking at N2. Okay, so we have 12.5 grams, and we're going to do some conversions here. We use the molar mass. So we have 1 mole N2 over 28.02 grams. And then we use this conversion, 181 kilojoules over 1 mole of N2. So the grams cancel, the moles N2 cancel. We do the math, and you should get 80.7 kilojoules. Okay, so that's the amount of heat associated with this reaction. One thing I want to emphasize here, it says heat is consumed. Consumed is because it has a positive sign. You want to be aware positive is endothermic, so positive is consumed, it's used up. That heat is going into the reaction as it takes place. If it had been negative, it would be released. It would be coming out of the reaction as it takes place. So just be clear about that distinction. Okay, this is the end of section 6.7. It is also the end of module 6, our longest module to date. Ask any questions related, so go ahead and work on worksheet 6.7 and ask any questions on the discussion board related to this material. If you haven't found a way to do anything on the discussion board yet, please do so now, and then feel free to start the online homework. I should also mention that this is the last module before the first exam. So at some point, the review material for that exam should be available. Feel free to jump on top of that, start getting ready for that exam as soon as you like. So there will be some information of that available as well. Look for that maybe ahead of when you would start looking for new material normally if you are done with this module ahead of schedule.